Assalamualaikum warahmatullahi wabarakatuh. My name is Amalia Binti Zamros. I am from Group 5 of Advanced Communication Technology Project with my another two group members, which are Ramizah Binti Zainul Azahar and Nurul Lyana binti Zarol Helmi, are going to present on design a small patch antenna at 3.5 GHz for 5G application. Introductions. 5G communication has been widely discussed as a future means of providing high data rate communications. The design testings for 5G communication system are dependent on an understanding of the propagation channels, necessitating a large body of channel measurements. 5G mobile systems are currently broadening their spectrum to support a high data rate. The 5G candidate frequency bands below the 6 GHz were widely discussed at the World Radio Communication Conference (WRC) in 2015. Among these, 3.5 GHz has received a lot of attention because it is widely accepted in most countries. As a result, the focus of this paper was on propagation channel characterizations in 3.5 GHz bands. The study goal is to create a small antenna that can operate 3.5 GHz for 5G applications. The antenna must be small enough to fit inside any new technology small communication devices. The goal will be to maximize data transfer by having high gain and efficiency. Next is antenna. Substrate, pitch, and ground plane are the three main components of microstrip antenna in 3.5 GHz band was designed. The substrate is designed with a box of FR4 proxy with a dielectric constant of 4.3. The height of the substrate with the respect of the z-axis of 1.6 mm. The ground plane is formed at the substrate bottom, resulting in the coplanar waveguide structure. The outer box is made of A assigned with radiation. These are the parameter design antenna for this project. Its major axis 22 mm, its minor axis 30 mm, matching line length 18 mm, matching line width 2.9 mm. Height of substrate is 1.6 mm. Other than that are substrate width with measurement of 48 mm, substrate length of 25.2 mm, ground length of 48 mm, and lastly ground with 10 mm.
Okay, first of all, we will open the CST file, tickle, and then antenna, planar, time domain, and this one is
frequency minimum 2, frequency maximum is 4.5, A field, H, and far field for default is 3.5. I need to wait for a while. As you can see here, it's a cubic. Okay. If I turn around, you can see all the sides is equal. For the working plane, and I click break and name it as sub. Negative A per 2, B per 2, A per 2. And for the X, mat is H. For the material, we need to use RF4C.
Add one more brick for rectangular. For X minimum, A over 2 minus 11.5, because we want to have an equal rectangle. And that for X max, A over 2 minus 18 minus 6.5, Y minimum negative 2. And for the parameter is 0.035. Cylinder shape, and then choose elliptical. elliptical cylinder, and then choose elliptical cylinder, and then rename as AEL. Okay, then I add one more brick. One ground and also ground fit, click boolean, then it will be like this. Okay, almost done. Then wait, I want to find the macros. Okay, found. So click solver, parts, and then calculate parts extension coefficient. Then simulation and got the output for S parameter like this, and this is the warfare looks like. So that's all. Thank you.
So I'm going to continue for the result and finding. For result and finding, we have two views of the design antenna, which is figure 1 showing that the back view of the design antenna and figure 2 showing that the front view of the design antenna. Directivity is a fundamental antenna parameter which describes on how much the radiation emitted in a specific direction. If antenna is designed to radiate in a specific direction, the directivity is considered as critical. So, as you can see here, figure 3 showing the radiation of the antenna, which the antenna's main lobe has a directivity of 5.12 dBi at 76.9 degrees in theta direction. The side lobe level is negative 12.9 dB. Figure 4 showing the return loss or S11 parameter of the design antenna. At a very steady state, the scattering parameters define the electrical behavior of a linear electrical system when it is stimulated by electrical signal. The S parameter in electrical system represent the input and output relationship between the ports. As is generally known, the resonant frequency and return loss may both be calculated from the patch of S11 curve. So as a result, the resonant frequency achieved is 3.025 GHz with a return loss of negative 32.219 dB. This demonstrates that the antenna has a very low return loss when operating at 3.5 GHz. This means that the antenna will transmit a significant amount of the signal. The ratio power produced by the antenna from a far-field source on the antenna's beam axis to the power produced by the hypothetical lossless isotropic antenna can be seen as antenna gain. At working frequency of 3.5 GHz, the antenna has a gain of 5.01 dB. The efficiency of the antenna is negative 0.1562 dB or 96.25%.
Conclusion. To sum up, a tiny elliptical antenna has been built for use at 3.5 GHz for the 5G applications in this project. The antenna physical dimensions are 25.2 times 45 mm square. At 3.05 GHz, it has return loss of 32.219 dB. The gain of the antenna is 5.01 dB. The antenna's efficiency is quite high, which is at 96.25%. That's all from our group. Thank you for listening.